Hello friends. So today we are going to discuss few questions from the year 1985, and we have 1987 and 1986. So we have two questions from 1985 as well as two questions from 1986. There is only one question from 1997. So total we are going to discuss these 5 questions, or you can say 5 PYQs. So 2 are from 85 and 2 are from 1986. So first one is from 1985, and in this question it is asked that a rectangular loop carrying a current I is situated near a long straight wire such that the wire is parallel to one of the sides of the loop and is in the plane of the loop. If a steady current I is established in the wire as shown in the figure, the loop will be. So basically we have to find out how the loop, which is carrying a current small I, is going to behave in the presence of a wire which is carrying a current capital I. So in this case, let us say we have this loop as A, B, C and D. So total there are 4 sides in this loop, and 2 sides AB and CD are parallel with the given wire, and 2 sides BC and AD are perpendicular to the given wire. Okay. So based on this configuration, we are going to find out what will be the force as well as magnetic field. So we already know the standard formula for the magnetic field due to a long straight wire. You know, magnetic field at a perpendicular distance R from a long straight wire carrying current capital I, and that magnetic field is given as B is equal to, it is given as B is equal to mu naught I upon 2 pi R. And now it has 4 sides. Okay. So we can find out the forces on different sides of the loop. Forces on the different sides of the loop. So it has 4 sides, and these 4 sides are AB, BC, CD and DA. So these are our AB, BC, CD and DA. And in this case, 2 sides AB and CD is parallel to straight wire, and the remaining 2 sides, which are BC and dA are perpendicular to straight wire. Are perpendicular to straight wire. And from the figure we can clearly see that the wire AB is nearer to the straight wire. Let us call this distance as R1, and CD is farther from the straight wire. Let us call this distance as R2. So first of all, we are going to find out the force on the side AB. AB, and here the direction of current in the straight wire is upward, and similarly the direction of the current in the AB side is also upward. So they both have same direction. You can say that straight wire and AB carry current in same direction. Current in same direction, and therefore they attract each other. They attract each other. So we can find out force per unit length. Force per unit length, and for side AB we can write this as FAB will be equal to ILB. We substitute the value of the magnetic field, and here the distance is R1. So you can say the force on AB will be equal to IL mu naught I upon 2 pi R1, and this will be our attractive force. Attractive force. Now let us find out for the farthest one, which is our CD. Force on side CD, let us call this as, and it will be giving us same formula, but IL mu naught I upon 2 pi R2, and this will be repulsive force. You can say repulsive force. And also we have that R2 is, R1 is greater, R2 is greater than R1. R2 is greater than R1. So you can say that magnetic field at CD is weaker than at AB. So based on this, we can say that force because of the side CD is less than the force at the side AB. So which basically means that attractive force on AB is going to dominate the repulsive force. You can say attractive force on AB will dominate repulsive force on CD. Now we have two wires, forces on the side which are perpendicular. So we can say forces on side BC and DA, and these are perpendicular to straight wire. Straight wire. So it means both the wires. So magnetic magnetic field exerts a force perpendicular to both the current direction and the field. So from here we can say that the magnetic field exerts a force perpendicular to both current direction and the field. So in both the cases there will be equal and opposite force. So means that you can say, since both sides experience equal and opposite forces, they cancel out, or we can say balance. And we can write that force on BC will be in opposite to force on our DA. So because of this, the net force due to BC and DA is 0. Therefore, net force due to BC and DA is 0. Now we can find out net force on the loop. Net force on the loop, let us call that F net. And like I said, the force because of AB is greater than force because of CD. So we subtract them, we get this IL, and we have here mu naught I upon 2 pi R1 minus mu naught I upon 2 pi R2. So the net force will be attractive. So we can say our F net is greater than 0. So loop moves towards the wire. towards the wire, or we can say attractive force. Attractive force. So the options that are given to us, option number C is the correct option, which states that it moves towards the wire. So you can say option C is correct. Correct. We come to the next question. And here it was asked in the year 1987, and it states that two long straight parallel wires are 2 meters apart, perpendicular to the plane of the paper. The wire A carries a current of 9.6 ampere directed in the plane of the paper. The wire B carries a current such that magnetic field of induction at the point P at a distance 10 upon 11 meter from the wire B is 0. Find. So we have 3 questions based on this entire description. In the first one, it says that the magnitude and direction of the current in wire B rather, the magnitude of the magnetic field of induction at point S, and finally the force per unit length on the wire B. So we have the figure. We have wire A and wire B, and wire A is carrying a current which is, you can say, into the plane of the paper. So that's why it's marked at X, and we have a point P which is 10 by 11 meter from B, and it says that at this point P the net magnetic field is 0. So we are going to start from this point only. So we say that the magnetic field at point P is 0, and from this we can make a conclusion that the magnetic induction at point P carrying, because of the two wires A and B, should be equal and opposite. Okay, so it means for wire A the current is in the downward direction, so therefore the wire B should be carrying a current which is opposite to that of the wire A. So you can see from here that the magnetic field at P produced by current carrying wires should be equal and opposite. So which means that the direction of current in B, the direction of current in wire B must be opposite to that of wire A. So that is directed upward and perpendicular to the plane of paper. So therefore, for wire V, we can draw something like a dot. So this means that the direction of the current is in upward and perpendicular to the plane of paper. Now we can find out, or we can write the magnetic induction at point P due to wire A. Magnetic induction at P due to wire A, let us suppose that is given as B1, then B1 will be equal to mu naught. Let us suppose current is given as I1, and this becomes 2 pi R1. So from A, it is having a current I1, and distance of this point P from A is, let us suppose, is given as R1. And similarly, we can find out for current for wire B. Similarly, for wire B, let us call that as B2, and that will equal mu naught I2 divided by 2 pi R2. And here B is carrying a current of I2, and this distance is our R2. And net magnetic field at point P is 0. Net magnetic induction at point P is 0. So therefore, we can write that B1 is equal to B2. We substitute the respective equations. We can write this mu naught I1 divided by 2R1 is equal to mu naught I2 and 2 pi R2. Here mu naught 2 pi cancels out. So this gives us that our I2 will be equal to R2 by R1 and multiply by I1. And we can find out our R2. Rather, R2 is given to us. R2 is our 10 upon 11. R1 will be over 2 plus 10 upon 11, which gives us a 32 by 11. And I1 is also given to us. I1 is our 9.6 amperes. So substituting these values, we get our I2 is equal to 10 upon 11 divided by 32 upon 11 multiply by 9.6, and this gives us 3 amperes. So I2 is our 3 ampere, and direction is upward perpendicular. Now we come to the part B. And in this case, we have to find out the magnetic induction at point S. So we have to find out the magnetic induction at point S. And we can, let us say, this distance is our R1 prime, and this distance is our R2 prime. From wire A, it is R1 prime. So we can say the magnetic field produced by wire A at S. Let us call that B3 is equal to mu naught I1 divided by 2 pi R1 prime, and we know all the values. So if we substitute all the values, we can say that our B3 will be coming as 12.12 into 10 to the power minus 3 minus 17 Tesla, sorry. Similarly, we can find out the magnetic field produced by wire B at S. Magnetic field produced by wire B at S. Let us call that as B4, and B4 will be equal to mu naught I2 divided by 2 pi, and this is R2 prime, and we get our B4 will be equal to 5 into 10 to the power minus 7 Tesla. And if we draw, or we can say if we check this triangle, this is our A, B and S, and we are AB is given as 2 meter, 1.6 and 1.2. AB is our 2, this is 1.6 and 1.2. So if we see this triangle closely, you can say in triangle ABS we have that our AB square is equal to AS square plus BS square. AS square plus BS square, and 1.6 and 1.2. Yeah, 1.6 and 1.2. So which means that angle ASB is our 90 degree. You can say angle ASB is our 90 degree. Therefore, you can find out the net magnetic field. The net magnetic field at S, let us call that as BS, will be equal to B3 square plus B4 square and the square root, substituting the values. I think there is some, yeah, there is, this is wrong. This should be our 4, my mistake. So if we substitute the values, we get this as 12 into 10 to the power minus 4 whole square plus 5 into 10 to the power minus 7 whole square. So we get our BS will be equal to 1.3 10 to the power minus 6 Tesla. And the last part, we have to find out the force per unit length on wire B. Part C, force per unit length on wire B. Let us call that as F. So we can say F is equal to mu naught current in both the wires A and B, and the distance between the two wires, that is RAB. And we simply substitute the values. We get that F will be equal to 2.88 into 10 to the power minus 6 Newton per meter. So this was the question. And the next one, we have that a beam of protons with the velocity 4 into 10 to the power 5 meter per second enters a uniform magnetic field of 0.3 Tesla at an angle of 60 degree to the magnetic field. Find the radius of helical path taken by the proton beams. Also find the pitch of the helix, which is the distance traveled by a proton in the beam parallel to the magnetic field during one period of rotation. So in this case, we are given that a proton enters a magnetic field of this at an angle of 60 degree. And direction of magnetic field is not given, but it said that the magnetic field is uniform. So it is going to travel some helical path because of this angular projection of the proton inside the magnetic field. So we can resolve the velocity into two components. Resolve the velocity. So we're going to have two components. First one will be perpendicular to magnetic field. Let us call that as V perpendicular. This causes the circular motion. And the second one is parallel to magnetic field. Parallel to magnetic field. This causes the linear motion along the field. Linear motion along the field. So we can find out these two components. We can say our V perpendicular will be equal to V sine of theta. This comes as 4 into 10 to the power 5, and we have here sine of 60, and this comes as 2 square root of 3 into 10 to the power 5 meter per second. And V parallel will be equal to V cos of theta, and that will be coming into 2 into 10 to the power 5 meter per second. So if we require, we can just draw a, so suppose this is a velocity making an angle of 60. Two components, we have this as V parallel and this will be V perpendicular. Next, we are going to find out the radius of the helical path. Radius of helical path, and in this case, for the radius of helical path, the velocity, which is V perpendicular, which forces the proton to move in a circular motion. So because of this, the force of the magnetic field will be producing the necessary centripetal force. Okay. So we can say the radius R of circular motion is given by the centripetal force balancing the magnetic force, given by the centripetal force balancing the magnetic force. So therefore we can say F magnetic will be equal to F centripetal. And we can write that a Q V perpendicular magnetic field will be equal to M V square perpendicular divided by R. So this gives us that our R is equal to M V perpendicular divided by magnetic field, because here this goes with this square, and we simply substitute the values. You can say our R is equal to 1.67 into 10 to the power minus 27. V perpendicular is 2 square root of 3 into 10 to the power 5, and charge is also there, QB. And we have 1.6 into 10 to the power minus 19, and this is 0.3. So this radius we can say is approximately equal to 1.2 centimeters. Now we can find out the time period of revolution. Time period of rotation, rotation, you can say that our T is equal to 2 pi m divided by charge multiplied by magnetic field. We substitute the values, we get 2 pi multiplied by mass is our 1.67 into 10 to the power minus 27. Charge is 1.6 into 10 to the power minus 19. Magnetic field is 0.3. So this gives us that this time period of rotation is approximately equal to 2.19 into 10 to the power minus 7 seconds. And from this we can find out the pitch. So pitch will be dependent upon the, because it on the linear velocity, that is V parallel. So we can say pitch of helix P is equal to V parallel multiplied by the time period. We substitute value, we get P is equal to V parallel is 2 into 10 to the power 5. Time period is our 2.19 into 10 to the power minus 7. This gives that the pitch is approximately equal to 4.38 centimeters. And the next question we have, which was asked in the year 1986, and it states that two thin long parallel wires separated by a distance b are carrying a current I amperes each. The magnitude of the force per unit length exerted by one wire on the other is. In this case, we are going to start with the magnetic field, and then we are going to use, you can say, the force equation, and that will be leading us directly to the answer. We start with the magnetic field. We say magnetic field due to one wire, and that is our B is equal to mu naught I upon 2 pi B, and we can find out the force. Force on the second wire, on the second wire, that will be for F is equal to ILB sine of theta. And where this theta is the angle between the current direction and magnetic field, so theta will be at 90 degree. So our sine of 90 will be giving us a 1. So we substitute the value of formula for magnetic field. So we can say the force is equal to IL. We have this mu naught I upon 2 pi B, which comes as mu naught I square L upon 2 pi B, and we are supposed to find out the force per unit length. Force per unit length, that is our F upon L will be equal to mu naught I square upon 2 pi B. So this is our final answer, and the option number mu naught I square upon 2 pi B, option number B is the correct one. Option B is correct. And in the next question, we are given that a proton moving with a constant velocity passes through a region of space without any changes in its velocity. If E and B represent electric and magnetic field respectively, then this region of space may be. This is basically a multi-correct option, and the important thing here is that it says that without any change of the velocity. So first of all, we are going to write the formula for the force because of electric field as well as magnetic field, and based on this we can draw certain conclusions. So we start with electric force. That is our Fe will be equal to charge multiplied by the electric field, and if there is only, you can say, non-zero electric field, then the proton will tend to accelerate. Okay. So from here we can just write that in non-zero electric field would exert a force on proton. Causing it to accelerate. Unless counteracted. Counteracted. Similarly, we can write for magnetic force that is our Fp will be equal to Q V cross B, and In this case, it is, you can say, it will cause the change in direction. You can say it means magnetic force can change direction of motion. Direction of motion, and this direction of motion can be circular or it can be helical trajectory. So in the question it is said that for constant velocity the proton is moving the constant velocity, so it means either B should be equal to 0 or it should be arranged in such a way that it cancels any force that is being from the electric field. You can say for constant velocity either B is equal to 0 or arranged such that it cancels, or we can say balances, any force from E, any force from the electric field. So therefore, let us check the options that are given to us one by one. So we have case 1. In this case, both electric field and magnetic field are 0. So because of this, you can say that the force due to electric field is 0 and force due to magnetic field is equal to 0. So there is no force on the proton. So it is going to move with a constant velocity. See, since no force acts on proton, it will continue to move with constant velocity. Constant velocity. So the options which says both electric field and B and 0, so option number A is correct. Option A is correct. Let us say our case 2. In this case, if electric field is 0 and magnetic field is not 0, but velocity is parallel or anti-parallel to B. Velocity is parallel or anti-parallel to our magnetic field. So the only force that will be acting will be because of this magnetic field. So we can say our Fe will be 0, whereas our Fb will be our QV cross B. And this V cross B, we said that the force is either parallel or anti-parallel to B, giving us the cross product is equal to 0. So because of this, can say that our magnetic force is also equal to 0. So in this case also, the electric field as well as magnetic field exert no force. You can say our no force due to electric field and magnetic field. So therefore velocity remains constant. Velocity remains constant. So let us check which of the option is there. So option number B is also correct. Option B is correct. And for case 3, both the electric field as well as the magnetic field is not equal to 0, but the net force is 0. Net force is 0, so which basically means force due to electric field plus force due to magnetic field is 0, or we can also say that force electric field is negative of the force of the magnetic field. And we already know force due to electric field is our QE, force due to magnetic field is our QV cross B, and for equal and opposite, for equal and opposite, our FE should be equal to our FP, or we can write this as QE is equal to QVB, which gives us that our electric field is equal to velocity multiplied by the magnetic field. And under this condition, we have our electric field plus magnetic field is equal to 0. So once again, no net force. Net force, therefore velocity is constant. And if we check any option that matches our discussion, option number D is the correct option. Option D is correct. So this completes all the questions that was asked in the year 1985, 87, 86. There were 2 questions of 85 and 2 questions of 86. These complete all the questions. Thank you.